Hello students, welcome to Veteach. So now in this session we'll be discussing a topic called Models of Evolution and Learning. So we already know that the major motivation for a genetic algorithm is biological evolution. So now how this evolution will take place on a human being. So that is what we are discussing now, right? So in many natural systems, individual organisms learn to adapt significantly during their lifetime. That is, animal, human being learn by themselves. They learn many things by themselves during their journey of life, right? So in the same way, here also, we in genetic algorithms, you need to design a model in such a way that once a model is generated, it should be able to learn something new when a new type of data set or new circumstances in the environment are present. So that is what we are discussing, and that should also be present in a genetic algorithm. That is the major intention that we discuss in this particular concept actually, right? So at the same time, biological and social processes allow their species to adapt over a time frame of many generations. So one interesting question regarding evolutionary systems is, what is the relationship between learning during their lifetime of a single individual and the longer time frame species level learning afforded by evolution? So these are the basic questions that are to be considered during the evolution of machine learning models or else learning models. So now we'll be discussing about one of the evolutionary technique which is called Lamarckian evolution, and here this particular evolutionary method was proposed by Jean-Baptiste and his lifetime was during the year 1744 to 1829. So this theory was based on the principle that all physical changes that occur in a human being during its lifetime are inherited by its offspring. That is, the changes that happens to us will also happen to its children. That is what is called happens to its offspring, right? So the development of an organ when used many times, right? So we will see example for this now. So this theory has been explained here. Suppose consider the organs which are used frequently by the organism means any object, animal, human being, so on, develop, and the characteristics that are used seldom are lost in the succeeding generations, right? So that is what is given here. So for example, a giraffe stretches its neck in order to have its food, and so due to this a nervous fluid will flow through its neck and it will enlarge. So the organs which the organisms have stopped using would shrink with time. So the more you work with the organisms, the better there will be development in that particular area. So that is what is given by Lamarckian. And despite this apparent biological fact, here recent computer studies have shown that Lamarckian processes can sometimes improve the effectiveness of a computerized genetic algorithm. That is, you can make not only human beings, you can make your AI machine, or else you can make your genetic algorithm based systems also to evolve based on a situation or during a period of time, right? So that is what is given by Lamarckian, and this is how we take it an analogy for a computerized genetic algorithms. And next we have Baldwin evolution. So what is Baldwin evolution? What Baldwin evolution says is, Baldwin effect is first demonstrated by Hinton and Nolan in the context of machine learning in the year 1987. So it is based on the following observation. So when this Baldwin effect was given by when this Baldwin effect was given by Hinton, these are the assumptions and final conclusions or else inductions that are generated. First assumption is, individual learning has no direct influence on the individual DNA. So individual learning is different, and the gene development in an organism is different. First assumption. Second assumption is, ability to learn reduces need to hardwire traits in DNA. That is, when you make your system learn new things, maybe physically doing those physical involvement of things or else physically making the component learn something will be reducing. So when we learn by ourselves, we can be doing better when compared to make you learn make you sit and learn something, right? So these are the two assumptions that are considered. So based on this, we can say that ability of individuals to learn will support more diverse gene pool, because learning allows individuals with various hardwired traits to be successful. But most of the times when you consider a computer, so rather than mental learning, some physical learning is also much required. So that is what is considered here. So more diverse gene pool will support faster evolution of existing gene pool. So the individual learning increases the rate of evolution. Whatever be the case, when you consider any machine learning technique over a period of time, or else based on the environment where your artificial intelligence system is moving on, anyways, based on the model that is embedded into it, it has to learn and it has to take decisions, right? So that is what is given by Baldwin or else Lamarckian evolution. So Baldwin effect says that, so some of the examples we take. So new predator appears in the environment, same. So whenever you develop some robot and whenever a new object comes in front of it which is not present during the training process, at that time also this AI machine has to do something. It should not do any wrong decisions, but it should take correct decisions and react accordingly, right? Individuals who can learn will be selected, right? So suppose if you consider n number of robots, physical objects, and when you give a new type of environment to it, so in that case you pick only those robots which are correctly responding, right? So that is, so how it happens? It happens only based on the algorithm that we give it. So increase in learning individuals will support more diverse gene pool. So resulting in it, and this Baldwin effect will result in faster evolution compared to Lamarckian effect. But, and this is a thing that can be applied to computer programming also. Maybe Lamarckian we cannot apply much to it. So this Baldwin effect can be more applied to computer programming. So possibly resulting in new non-learned traits such as instinctive fear of a predator. So all these are the different cases where we can apply this Baldwin effect in a AI or machine learning context. So now let's consider a neural network analogy. So let's consider a neural network. So in one experiment, they take a fixed number of weights, while other neural networks set to trainable. So what can we do from this? From this we can conclude that when there is no individual learning, that is when there is no concept of back propagation in a neural network, obviously the weights that you have taken initially will be the final thing. And when that is the case, obviously your neural network may not give you the best outcome. That is point number one. So the population failed to improve over time. So over a period of time, when there is no concept of adjusting weights for a neural network, maybe you cannot succeed further. Problem one, right? So when learning is applied in early stages, that is when we observe that your accuracy rates is dropping in that case, or else it is going overfitted, in that case what you will do, you usually apply dropouts. You apply some dropout nodes in a neural network, right? So when you apply the learning in the initial stages itself, or else at initial iterations itself, maybe you'll be getting the best solution in a very less time interval. So the population contains many individuals with many trainable weights, but in later stages what it will happen is it achieved high fitness with the number of trainable weights decreases in individuals. So whatever be the thing, you can apply the same to a neural network example, and that is what we have here, right? So that is what is given in this particular slide. So with no individual learning, finally we can conclude that with no individual learning, population fail to improve over time. So when individual learning is present and at the time of early generations, population contained many individuals with many trainable weights, and at later generations higher fitness can be achieved while the number of trainable weights decreases, right? So this is the simple example where you can apply Baldwin effect in a machine learning context, right? So this is about evolution. So next we have a small topic which is called parallelizing genetic algorithms. We already studied in the first slide that one important motivation of genetic algorithms is it can be easily parallelized. So how can we parallelize a genetic algorithm? Just we have some intro, we don't have in depth now. So genetic algorithms are naturally suited for parallel implementation, and the number of approaches to parallelization has been explored here. So on the whole we can do two types of parallelisms. One is coarse grained and the other one is fine grained. So what do you mean by coarse grained approach? In a coarse grained approach you have a problem where that is not much divided into some subtasks, right? So we will consider a problem and finally we try to find solution for that particular problem. So the problem is divided into some tasks and given to processor for execution. Suppose consider you have an example in the concept of object oriented context. A simple account object holds the customer name. What fields it will have? It will have customer name, address, account balance, opening date, last date, etc, etc. So all these parameters, all these fields are embedded into only one class or else one object which is called account. Maybe what will happen is if there are so many attributes, it might be a problem. So it takes high computational time as the size of the task is big, right? So if you have only few accounts, in that cases it is okay, but if you are having hundreds and thousands of accounts, it will be very tough when you use a coarse grained approach for parallelism, and also the design will be complex. So to overcome that, we have one more which is called fine-grained approach. So what do you mean by fine-grained approach? Fine-grained, that is, you consider one problem, divide that problem into small tasks and apply, try to find out solution for small tasks and finally combine the solution. That is what we do, and each and every subtask will be executed at different cores of a processor or else at different processors of a multiprocessor system. So in a fine-grained approach, the problem is divided into smaller tasks and each individual is given each processor for computation. For example, an account object, the same example that we consider, holds balance, and we have one more object which is called customer object. It holds only name and address of the customer, and we have one more object which is called account opening. It holds information like opening date, close date, what is the information, what is the balance available in that, so on, right? So this is the example of a fine-grained approach, and the advantage of fine-grained approach is it takes very low computational time as the size of the task is very small, and designing of that model will also be very easy, right? So designing will be easy and computational cost will be less, right? So this is about parallelization of genetic algorithms. Thank you.